We have a session on human exploration right now. We're honored to have our first speaker as Jim Head, who is the Lewis and Elizabeth Shirk Distinguished Professor at Brown University. Jim has been a part of NLSI since we chose our first teams, and he's going to be talking about astronaut lunar surface exploration destinations. So Jim, take it away.
We don't seem to have control of the presentation here at Brown.
Momentarily.
Okay, our tech crew is working on it. Thanks.
Which account on Connect are you logged in as?
Sandra_Weissman at brown.edu.
Please start your webcam as well.
There we go. I see you, Jim.
Okay, this sounds great. So it's just a great pleasure to be here, and I think it's really important to have this incredible session where we talk about how it is to, in fact, reinvigorate and work on future human exploration of the moon and then onto other destinations. So one of the things we've tried to do here is take a look at a series of astronaut lunar surface exploration destinations and think about the new technology that's necessary to address the really amazing number of new and exciting and complex scientific problems that the last decade of exploration has given us. So, of course, we've gotten a lot of lunar missions. I mean, we've been lucky, many of us, to have lived through quite a lot of these missions in the 1970s, late 60s, and in that era there. There was a decade-long period when huge numbers were flown, in fact, even including humans, and this provided a baseline for understanding the context of how other planetary bodies besides Earth formed. And this, of course, is exemplified by this diagram here, where we can see a lot of the comparative planetology objects that this knowledge was applied to. In fact, now we're in a renaissance. So 2003 to 2013, really it's a rebirth of lunar science. It's just been incredible this decade. ESA, China's just about ready to launch their Chang'e 3. This year, Japan, India, United States with numerous missions, Russia, of course, and the X Prize, and basically Albert Einstein is purported to have said, upon the advent of nuclear energy and nuclear weapons, that everything has changed but our way of thinking, and I think that's really true for the moon as well. So we have the moon, and we have a lot of really incredible important information that's providing a renaissance in lunar exploration. And this provides us not just something about the moon, but also a context for comparative planetology, because it's the most well-studied body and we really should take advantage of that. So we've debated before about how to portray that. We've talked about the moon being a cornerstone, a keystone, and I think a touchstone is really good. It's a physical or intellectual measure by which the validity or merit of a concept can be tested. You know, essentially magma oceans. Do we find them on Mercury, on Earth? On Mars, you know, there's reasons why we might expect them, why not, etc. So these are the kind of things we need to think about and use the moon as basically a touchstone to measure these other concepts against. So we're at the end of this decade. It's 2013. We're in the last year of this kind of like renaissance, if you will. So where do we go from here? This is really a critically important question because a significant amount of our information came indeed from human exploration. So there's two basic things that we learned from all of this. First of all, in terms of the future that is, first of all, we can target more extensive exploration around existing landing sites. Now, it may seem like a waste to go back to a place we've already been, like the Apollo 15, 16, or 17 landing site, but look at what we can do with Apollo 15. We've thought a lot about this as part of our NLSI activities. So if we went back, we could address new questions raised by the analysis, 40 years of analysis of initial data collected by Apollo 15. So we know from the work of Ben Weiss and our colleagues at MIT that, in fact, the lunar magnetic field recorded significant variations in the history of the magnetic field, if you will, the rocks did. And there's a strong interest in going back to look at the rill, Hadley Rill, because it, in fact, records this in a series of observed basalt layers that we can see in the walls of the rills, both with the great L rock data, but also the data that Dave Scott took with a 500 millimeter lens. We also know something that we've discovered recently with Alberto Sol's work about the role of water in these water-rich green pyroclastic glasses, and really significant findings from there. But we don't know the context of that. We need to go back and really understand what the variability is and also what the source is. There's a whole host of other things here, like what does 15415 tell us about the deep crust? This is only one rock from there. There's a diversity of rocks that can be picked up at the site. We can actually see where they are now, in contrast to our planning before we sent the Apollo 15 crew. Highland stratigraphy, there's layering seen in the walls of the massifs. What's going on there? Is that a Serenitatis ejecta, as some people might have thought early on? And could be, okay? Imbrium basin ejecta. We know we have shocked norites, 15455. We need to sample more, look at the context, and understand what's going on. And of course, Maury stratigraphy of the basalts can be really looked at as a way to get at the sequence of filling of the Imbrium basin. So, was it flood basalts, or was there a series of basalts, et cetera? We can actually get at that now by going back to the Apollo 15 site. We know where to go and what to do. The second major part of this is we can target new sites and ask new questions. Obviously very fundamental. And as an example here, I just point to, there are hundreds of examples on the near side and the far side. But here we just take the central peaks of and the floor of Theophilus and Copernicus and ask new questions. Deepak Dhingra has two GRL papers, one of them about the central peaks of the areas near Theophilus, et cetera, which reveal some very interesting mineralogy and structure, as well as impact melt structure on the walls and floor of Copernicus. There's huge numbers of questions we can ask about these recent craters. The relative role of unshocked and shocked rocks, the origin of the olivine seen there, the origin of the spinel. Recent paper in Science talked about, hey, maybe, in fact, Jay Malash and his colleagues suggested that some of these unusual minerals may be meteoritic contamination. So, shown in the upper right there is, in fact, a central peaks of Copernicus. I could easily imagine myself spending 2 weeks there trying to address those problems, looking at the context of these features, et cetera. And then, of course, what's the origin of the central peaks? A really poorly known problem. Nobody's really looked at fresh ones for any length of time, like we could do at Copernicus. Melt sheet and placement. What's the chill boundary layer at the top look like? How is it different from what's going on below? And again, what about melt sheet differentiation? A really important question. So we now know where to go and we know what to do, because we have images from LROC where we can actually see the rocks we want to go get. We have data from InCube that tells us what the mineralogical variations are, so we can actually plan traverses like you wouldn't believe. So we know where to go and what to do. And so the whole point I want to make here is that we can now go back and really start thinking about doing design reference missions with the new data we have from this Renaissance and lunar exploration to get at where to go and what to do. And these new developments actually permit us to think about longer stay times, diverse mobility options, increased mobility and exploration radius, significantly more down mass and up mass, and including robotics in this to free up astronaut time for human exploration optimization, and also full lunar access. So what approach should we take for these design reference missions to underline this new generation of lunar science exploration capabilities? Well, we can look at the first one, which is the top-down approach, which is what Constellation was, and then contrast this to the bottom-up approach. This is a summary of Constellation. You can see, for example, the Orion spacecraft, the Altair lander in the middle, and of course, the Ares launch vehicle in the lower left compared to the Saturn V and previous launch vehicles. And you can also see, in fact, the lunar outpost on the middle right, which this was leading. This was a top-down approach. The statement was made, this is what we're going to do, and we're going to go. And most people aren't fully aware of the fact that the reason we were going to Shackleton Crater was because Constellation could not survive lunar night. Therefore, you had to go there. It wasn't to go get the volatiles. It was because you had to go there to survive lunar night. That's okay. Lots of good things to do. It's on the rim of the South Pole, Aitken Basin, et cetera. But what we really want is total global coverage, so we can go back to these other places which have shown us to be really scientifically interesting. So what about a bottom-up approach? Well, if we take a look at another way to go about this, NASA's really made some very important decisions which integrate and synergize human and robotic exploration. LRO is a good example of that. Moon Mineralogy Mapper, GRAIL, LCROSS, LADDI, and of course the NASA Lunar Science Institute, which has been really fundamental in getting this kind of structure and thinking together. So to paraphrase the President in a slightly different way, we've indeed been there, but we have absolutely not done that, okay? So what we decided to do was start with a proven architecture and improve upon it. So look at science and engineering synergism, the bottom-up approach. What are the scientific requirements, and how do you engineer these to success? So the key point here is that we went back and said, well, let's just go back and think, 40 years ago, Apollo, that was pretty good. That worked a lot. A lot of good things came back from that. Why don't we just take the bottom line Apollo architecture and then work together to define scientific goals and objectives and redesign the whole basic infrastructure to optimize, taking advantage of scientific and technological breakthroughs that have happened in the last 40 years. And believe me, there's been a lot. So our Brown MIT NLSI team, essentially we team with Brown, with MIT Aeroastro Department and the Earth and Planetary Sciences Department at MIT, and we started with a proven architecture. Apollo, it worked. We engaged Apollo 15 Commander Dave Scott, and we can say that, ask the question, what can you do with this new technology after 40 years? So one of the key things was Dave Scott, in a series of seminars here at Brown and also at MIT and joint MIT and Brown, Dave outlined the real details of how Apollo worked and how, from his point of view, things could be optimized to increase the scientific capabilities. Jeff Hoffman at MIT, a 5-time shuttle astronaut, is of course the key person at MIT who helped with the courses that we organized, etc. So Dave and Jeff and I and others organized these courses, and we had just an absolutely great time. The students were phenomenal. We also engaged our Russian colleague Sasha Basilevsky with his extensive Lunar operational experience, and we just had a blast doing this. Okay, so we had a bunch of seminars, as you can see here, and special conferences in which we took a look at how you would do these design reference missions. You can see how we would redesign like a 500-day mission or a long-range mission to Apollo 15, how we would go back to that and ask these kinds of questions. So at the end, you can see in the agenda, we're defining the scientific requirements, etc. And this was what set the engineers on their way to try to optimize to meet these scientific requirements. So our requirements were global access, that's a thought, extended stay time, maximize up mass, down mass, maximize mobility, robotic assistance for remote access, all the kinds of things that scientists absolutely want in their kind of naive ways. But then when you're working with engineers who really understand what it is that you're trying to do, and that's the bottom-up science and engineering synergism approach, they really converted these into some requirements that they then went out to see if they could meet. Do expeditionary missions up to 14 days, because we couldn't survive lunar night either, but you could be there for 7 to 14 days. In fact, global access was a requirement, all latitudes and longitudes, including polar areas and the far side. And a bare bones updated Apollo architecture where you retain the basic lunar orbit rendezvous concept and add Earth orbit rendezvous since there are no Saturn V's, and also incorporate modern functional designs and new technology and use existing or proposed launch vehicles. So this was just a lot of fun, these basic things. And so here's just one example of improvements to the lunar module. The diagram there shows the lunar module at the same scale as the Altair lander. You can see the Altair lander is huge, okay? We just used the lunar module and said, how can we increase the capability of this? And just a couple of things here. You can see the LOX LH2 used as the descent stage propellant gave us a lot more bang for the buck, so to speak. And we also changed structure of the tanks to structure and the tanks to carbon fiber. This had huge savings. This is the technology that wasn't even thought of back in those days, and yet has huge implications in savings. So they updated electronics and communication system, replaced battery with high-performance fuel cells. It was just big news to me that the main driver there was forklift fuel cell technology. Imagine that. Forklifts are what provided us with the technology push to get fuel cells that in fact made them so efficient that we saved huge amounts. Looking at the bottom there, 44% overall limb mass reduction for identical functions. So this is good news. That means that's more up mass, that's more down mass. Now, we also examined a question, why stage before landing? Okay, so this is the Altair lander with a crew habitat, ascent stage, and payload, and the empty descent stage, fuel tank. So you take a lot of mass down to the surface that we'd rather have as being scientific experiments or the ability to bring rocks back or whatever. So the MIT students, working with the Brown students, thought of another option, which was to stage the landing vehicle. You can see here the descent profile here, and as you undergo separation, basically the descent stage, it goes on a ballistic trajectory while the lunar module extends down to the landing site. Now, when we first thought of this, it was like, oh, this is really fantastic. We can actually get more mass to the surface, etc. And what the MIT people said, oh, we have a problem here. The impact, the descent module is going to be separated from the power module, and it's going to crash. So we have the distance that's going to crash, the impact distance, and we need you to help work a problem of whether ejecta from that is going to actually interfere with the landing. So we were busy doing that, and so, okay, doing the calculations, et cetera. It's going to be an oblique impact, blah, 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 blah. And we realized, oh my God, there's going to be a fresh impact crater within driving distance. And so this
Just about a minute left.
Got it. This didn't become just a way to get at this, to do this, but it became an actual scientific experiment in itself. So we could actually go to a landing site which would impact and eject material, and we'd be able to study fresh impacts essentially at each landing site and the ejecta from these as well. So again, this is a good example of the science and engineering synergism where the engineers created a solution which was actually a further opportunity for the science. So the bottom line here is that the Brown MIT NLSI class findings are listed here, and I encourage you to take a look at these details. I won't go over them in detail, but at each turn, down mass increase of almost 30% through the carbon use, increased bandwidth, better sensors, 60% of power recovered by using other ways other than radar GNC. For GNC, potential power upgrades, life support systems, 25% savings to the nominal emission, and the payload updated to 56% of original limb mass, and staging during descent, land with ascent stage only. All of these things resulted in huge, huge savings. So the human exploration mission is really, really plausible for a kind of Apollo-style architecture, not even having a Saturn V, but in fact engineering something with full lunar access, extended stay time, 7 to 14 days, and in fact a long, long capability on the surface, and much more return of mass to the surface and bringing of experiments down to the surface. We also looked at, to close here, at the capability of robotic technology. We had a bunch of seminars on other ways to explore Hadley Rill in terms of hopping, and Farah Albay and Phil Cunyo, two MIT students working on this project, really were able to give us examples of how we might sample the walls of the Rill using this new hopper technology that would be deployed during the landing, after the landing, and essentially be controlled not by the astronauts but by the ground. So this is a good example of the human-robotic synergism where the astronauts don't have to sit there and do anything with it. It just does it by itself, but it completely complements the exploration by humans and optimizes the science from this particular mission over the course of several weeks. This thing can go on for almost indefinitely. So just in summary then, the good news to me for human exploration is we don't have to do a top-down thing, which is hugely expensive and only goes to the South Pole. In fact, we have the capability here with this new technology, as demonstrated by these studies, to do a tremendous amount of excellent research all over the moon. And we can go back to places we've been before to optimize that, or we can go to the host of new places we've discovered in the last decade of essentially this renaissance in lunar exploration. So I just leave you with these thoughts that we now have the capability to really work hard from the bottom up to define scientific research, and all we now have to do is to convince people to actually do this. But the hard part is essentially done. The conceptual studies are that this is a real winner in terms of returning humans and robots to the moon in the foreseeable future. Thank you.
Excellent, Jim. Thank you very much. Just great. So we have a few questions. I'm just going to take one of them live here, but if you wouldn't mind answering the rest of them in chat, we can all see your answers to them. But there's an intriguing one about would you want to go back to the Apollo 18, 19, or 20 sites?
You know, I think we'd have to, sure. So among the landing sites of Apollo 18, 19, and 20 were Marius Hills, Tycho crater, floor of Copernicus crater, for example. There were some really good sites. So actually, Copernicus crater floor actually did traverses in 1967 or something like that for exploring the central peaks of Copernicus with a lunar landing. So yeah, there's lots of places to go. I don't have any preference for those. I think we have to look at all the new data we've gotten to address that. But the exciting thing is we have full lunar access. We have full lunar access. So, you know, anywhere you want to go, you can go. And that sounds like a great debate to have in the scientific community.
Excellent. All right. Well,